So far, we're able to solve a fairly limited set of exponential equations. We know how to solve exponential equations when the base is the same on both sides. To solve an equation like that, we simply note if the bases are the same and the results are the same, then the exponents must be the same. We also know how to solve equations where there's just one exponential expression. To do that, we isolate the exponential expression and then rewrite the equation in log form. What if we have an equation, however, in which there's more than one exponential expression, but the expressions have different bases? Now we're going to see how to solve an equation like that. Here's an example of an exponential equation where we have different bases on each side of the equation. Right, on the left-hand side, the base is 2. On the right-hand side, it's 3. How would we go about solving this equation? Well, we need to get those x's out of the exponent. Right? The x in the exponent is causing us a problem. And now that we have our log rules, we have tools available to us to get a variable out of the exponent. Our first step will be to take the log in any base that we like of both sides of the equation. Usually we'll choose either the common log or the natural log, because that'll make our lives easier as concerns the calculator. I'm going to choose to use the natural log here, partially because that's my favorite log, and partially because it has one less letter. But you can choose whatever you'd like. So I'm going to take the natural log of both sides. And there's no problem with taking a log here, since these exponential expressions will always be positive numbers. Now that we've done that, we'll use the log rules to get the variable out of the exponent. So on the left-hand side, we have the natural log of 2 to the x. That'll be x times the natural log of 2. On the right-hand side, we have 3 to the power x minus 1. That'll be x minus 1 times the natural log of 3. Now the thing to notice is that these logs are just numbers. If I wanted to, I could put those into my calculator and get a decimal approximation, or I could just continue to work with those logarithm expressions, and if I want a decimal approximation, get that at the end. That's what I'm going to do. But I have to remember that ln2 and ln3 are just numbers. So now I'm going to just solve normally. Right, I'm down to a linear equation now. So let's see. On the right, I need to distribute because I need to get rid of these parentheses. So I'll have x times ln2 equals x times ln3 minus 1 times ln3 is ln3. Now I need to get my x terms on the same side. Now, this next move is just combining like terms, but you can think of it as factoring out the x if you like that better. And finally, we need to divide both sides by this number. So we'll divide both sides by ln2 minus ln3. And we're left with negative ln3 over ln2 minus ln3. Now, if we really, really wanted to, we could use log rules to rewrite this. But we usually won't bother. We'll only bother with that if we have a very specific goal in mind. If we want an exact answer, we could leave our solution written just like this, leaving our answer as the exact value in terms of logs. Or we could use our calculator to get a decimal approximation. If we did that, we would get x is about, we'll have in our numerator negative ln 3, and then our denominator is ln 2 plus ln 3. Oh, it looks like I hit the wrong button. I meant minus back there. Negative ln 3 over ln 2 minus ln 3. We get x is about 2.71. If we want to check that, we hope to see 2 to the power 2.71 approximately equal to 3 to the power 2.71 minus 1. So 2 to the power 2.71, that's 6 and a bit. 3 to the power 2.71 minus 1, that's very, very close. We wouldn't expect it to be exact because we rounded that answer, but those are close enough that we think that that is the solution. Now, we have not solved every equation involving an exponential expression by any means. In particular, we have not seen how to solve an exponential equation that includes two exponential expressions and other terms. Say if we have something like 2 to the x equals 3 to the x minus 1, then this technique of taking the log of both sides isn't going to help us. In general, if we have two exponential expressions and other terms, in general we'll need to use numeric methods, so some sort of trial and error or some sort of computational process to get usually an approximation for an answer. Right? In this example, we can just guess. The solution is x equals 1. We can tell that because 2 is equal to 3 minus 1. But taking the log of both sides wouldn't help us because the log couldn't split up that difference. I'm going to give you one of the ones that we can solve, one with exponential expressions on both sides, to try now. So the equation is 5 to the power 2x minus 1 equals 3 times 2 to the x. Pause the video and try this now. Okay, so we have exponential expressions on both sides. We want to start by taking the log of both sides. And again, I'm going to choose the natural log. And now we want to use log rules to rewrite both sides in such a way that we get the variable out of the exponent. So on the left, that's just a single step. 2x minus 1 times the log of 5. On the right, first we need to split up this multiplication. So that'll be log of 3 plus log of 2 to the x. And then that second term becomes x times log of 2. Now, remembering that this log 5, log 3, log 2, those are just numbers. We're now going to just solve this normally. On the left, we have to distribute 2x times ln 5 minus 1 times ln 5. And now we'll collect the x terms on the left. Collect the not x terms on the right. Now on the left, we're really combining like terms, but we can think of that as factoring out an x if we prefer. And finally, we'll divide both sides by this thing. So this is the exact answer. If we prefer a decimal approximation, we can say ln 3 plus ln 5 over 2 ln 5 minus ln 2. We get x is about 1.07. We might also choose to check 5 to the 2 times 1.07 minus 1. We want to know, is that about the same as 3 times 2 to the 1.07? So 5 to the 2 times 1.07 minus 1. That's 6 and a bit. 3 times 2 to the 1.07. Those are very close. That answer is a good approximation.